Okay, so in this video, we are considering other examples of the following question. Are the following vectors linearly independent or dependent? In this example, we are considering three vectors as rational functions. So here, our vector space could be taken as the space of all functions. So we can call this V, and we'll take f, where f is a function from the real numbers to the real numbers. So if you take all functions from the real to the real, you have a vector space, and clearly rational functions are functions. And so we can think of these three rational functions as vectors because they are elements of the large vector space that contains all real functions. We could call this v1, the first vector, the first element of our vector space, then v2, and then v3. As always, when we consider this question, we have to look at a linear combination of our three vectors, giving the zero vector from the vector space. Well, and we ask, well, how many solutions are there? Obviously, if we set C1, C2, and C3 to be all 0, we get the zero vector. So the trivial solution C1 equals C2 equals C3 equals 0 is always a solution. If it is the only solution, then the vectors are linearly independent. If we can find more than the trivial solution, that is one solution where at least one of the coefficients is not 0, then the vectors are said to be linearly dependent. So let's rewrite our three rational functions. So we will have C1 times the rational function x over x plus 1 plus C2 times the rational function 1 over x minus 4 plus C3 times the rational function x cubed over x minus 1. And this is equal to the zero vector. The zero vector is the zero element of your space. As we have a space of real functions, the zero element is obviously the zero function. The function is equal to 0 for all real values of x. Now here we have two options. We could, if we wanted to, combine this linear combination of three rational functions into a single rational function by putting these over a common denominator. Then we would have a single fraction being equal to 0 for all values of x. That is only possible if the numerator of our fraction is equal to 0, and that would give us a linear system. And we can solve the linear system to determine whether or not our three functions are linearly dependent or independent. We can actually do here simpler, taking advantage of the fact that this equality is supposed to hold for all values of x. The question is, well, how do we take advantage of this fact that no matter which value of x you take, this equation must always be equal to 0? Well, let's think about it this way. What if we let x, say, approach -1 in the linear combination? Let me rewrite the linear combination. So C1 x over x plus 1 plus C2 1 over x minus 4 plus C3 x cubed over x minus 1, and that is 0 for all values of x. So as we're letting x approach -1, this will always be equal to 0. Let's look at these two terms first. Well, as x approaches -1, this will approach 1 over -1, -4, -1 over 5. So this will approach quite simply -c2 over 5. The key is this will be approaching a fixed constant. The same goes for our third rational function. As x approaches -1, x cubed approaches -1, -1, -1, -2, and we'll get -1 over -2, therefore positive 1/2. And so this term will approach c3 over 2, which is also a fixed constant. What about this now? As x approaches negative 1, x goes to negative 1 on top, x plus 1 will shrink to 0. Now, depending on whether you approach negative 1 from the left or from the right, we'll either get here negative 1 over positive 0 case, which will give negative infinity, or negative 1 over negative 0 case, which will give us positive infinity. But either case, the x over x plus 1 will be approaching plus or minus infinity. Now think about what's going on here. As we're letting x approach negative 1, this term approaches a fixed constant. This term approaches also a fixed constant. So both of these are bounded. They're finite values. But if you think about it this way, what if c1 was not 0? If c1 is not 0, this whole term will approach positive or negative infinity. How can one term be blowing up to positive or negative infinity, the other two being constant, and the result of the sum be 0? This is impossible. If this term blows up to positive or negative infinity, because both of these are bounded, the whole thing would blow up to positive or negative infinity. But this can't be, because this is equal to 0 for all values of x. So the only possibility here is that c1 is equal to 0. This term cannot be here. And so c1 equals 0. And you say, well, why not repeat by looking at the second rational function and letting x approach 4 now? And I'll go more quickly over this one. You see, if you let x approach 4, this will approach 4 cubed over 3, so this will be a constant. This will approach 4 over 5 c1, which will also be a constant. So both of these remain bounded as x approaches 4. But now this will give us a 1 over 0 case. So, as we approach 4 from either the left or the right, this term will approach positive or negative infinity. But these two terms will remain bounded. This term, if c2 is not 0, will blow up, but the sum is always 0. This is impossible, as these two terms remain bounded as we are approaching 4, and the term 1 over x minus 4 blows up to positive or negative infinity. The result can't be 0. And so this term can't be here, therefore c2 must be equal to 0. And as you can imagine, we will prove that c3 must be 0 by letting x approach 1. If you're letting x approach 1, this will approach 1/2 c2. This will approach negative 1/3 c2, c1, sorry, 1/2 c1, negative 1/3 c2. So both of these functions remain bounded as x approaches 1, but this will give you a 1 over 0 case, which will blow up to either positive or negative infinity. Well, so if c3 is not 0, this term blows up, these two remain bounded, the sum can't be equal to 0. Therefore, this term can't be here, therefore c3 must be equal to 0. But look at this. The only way to have a linear combination of our three rational functions being equal to 0 for all values of x is for c1 to be 0, c2 and c3 to be 0. Therefore, the only solution is the trivial solution, where all the coefficients are equal to 0, which proves that our three rational functions are linearly independent. As the only way to obtain the zero element of our space through a linear combination of our three rational functions is with the trivial solution as the unique solution. We must set every coefficient to be equal to 0. And this proves that we have linear independence. Let's do two more examples. We will consider again our vector space being the space of all functions. And what if we consider trigonometric functions? Say we consider secant squared of x, tangent squared of x, and 1. So you can think of this as being the first vector of your space, v1, then this being v2, and this being v3. Again, the space of all functions is a vector space. These are functions. And so we can think of these three functions as vectors from the vector space of all functions. Well, at least in our case, of all real functions. And now the question is, well, same as before, are these three functions linearly independent or dependent? There are several ways to look at this, but if you remember the result that said that vectors are linearly dependent if and only if at least one is a linear combination of the others. So vectors are dependent if somehow there is a connection between them. So here we can be quite sneaky. We can ask, is there a known connection between secant squared, tangent squared, and the constant function 1? And the answer is yes. If you remember, 1 plus tangent squared is equal to secant squared. And now you can think of it in two ways. Secant squared is a vector in our list, and it is a linear combination of these other two vectors. Secant squared of x is 1 times 1 plus 1 times tangent squared. As secant squared is a linear combination of tangent squared and 1, our three elements are linearly dependent. Or you can think of it this way. Subtract secant squared on both sides and you will have, and I will write it this way, 1 times the vector 1 plus 1 times the vector tangent squared of x. As I subtract secant squared, I will get negative 1 times secant squared of x. And this is constantly equal to 0, the 0 function, therefore the 0 vector of our space. And you can see this is the first coefficient, c1, the second coefficient, c2, and the third coefficient, c3, of our linear combination. So we have a multiple of 1 plus a multiple of tangent squared plus a multiple of secant squared being the 0 vector of our space. And as we can see, this is clearly not the trivial solution. None of the coefficients are equal to 0, which proves that our three functions, secant squared of x, tangent squared of x, and 1, are linearly dependent. So the idea here again was to think of the really useful result that says vectors are linearly dependent if and only if at least one is a linear combination of the others, which implies that there is somehow a connection, a relation between our vectors. And this was the very well-known relation between 1 tangent squared and secant squared. Let us do one last example, considering now three functions, y equals x, y equals ln of x, and y equals e to the x. The question is the same. Are these three functions vectors linearly dependent or independent? Well, as always, we consider some linear combination of our elements, of our vectors, being equal to the 0 vector of our space. As, again, we have functions, they are living in the large vector space of all real functions. Therefore, the 0 vector is the 0 function. So this must be equal to 0 for all real values of x. Another question is, how do we prove or how do we decide whether or not these three vectors are linearly independent? Well, once again, we will take advantage of this fact. This equality must be true for any real value of x. Well, there are several ways of attacking this problem. If we wanted to, we could let x approach 0 from the right. Let's see what happens to our linear combination. c1x plus c2 ln of x plus c3 e to the x, and this must be equal to 0 for all real values of x. And so as we are letting x approach 0 from the positive side, this equality must always be satisfied. Well, what happens to c1 times x? As x approaches 0, c1 is a constant, and so c1x will be approaching 0. Now, e to the x, as x goes to 0, approaches e to the 0, which is 1. And so this will approach c3. So you see that this term shrinks to 0. This term approaches c3, which is a constant. So the sum of these two terms, as x goes to 0, will simply be c3, therefore approaching a fixed real value. What about c2 ln of x? If you remember the graph of ln of x, it looks something like this. And so, as x approaches 0 from the right, ln of x we can see goes to negative infinity. But now there's a problem. If c2 is not 0, either positive or negative, the term c2 ln of x will be approaching positive or negative infinity as x approaches 0 from the positive side. But as these two terms remain bounded, the result can't be 0. Because these are bounded, this one blows up, the whole thing must blow up. That's a contradiction, therefore c2 has to be equal to 0. Okay. So now we can rewrite our linear combination. We see the only way for this equality to be true for all real values of x is for c2 to be 0. So if c2 is 0, this term goes away, and our combination ends up being c1x plus c3 to the x equals 0. Once again, this is true for all real values of x, as the 0 here is the 0 vector of our space, and this is the 0 function. How can we proceed here? Well, what we can do is divide across by e to the x. E to the x is always positive, and so we can divide across the equality, which will give us c1x over e to the x plus c3 equals 0 again for all real values of x. And once again, we're going to let here x approach positive infinity. Not once again, sorry, but we've done this before, or actually, no, we haven't. This will be a first time. We've let x before approach -1, 4, 1, x approach 0. Now we will let x approach positive infinity. Let's look at this term for a second. If we take the limit as x goes to infinity, x over e to the x, and this will be a nice review of L'Hopital's rule. As x goes to infinity, x goes to infinity, e to the x goes to infinity, so we have an infinity over infinity case. We can use L'Hopital's rule, which works, if you remember, for 0 over 0 cases and infinity over infinity cases. And L'Hopital's rule says that the limit will stay the same. So x is still approaching infinity. But now we are replacing each function by its corresponding derivative. Replacing x by its derivative, which is 1. Replacing e to the x by its derivative, which is itself. But now you get 1 over infinity, which is simply equal to 0. And so if we let x approach positive infinity, then x e to the x approaches 0. Therefore, this term shrinks to 0, and we're left with, quite simply, c3 is equal to 0. So now we're down to coefficients. If c3 is 0, we are left with c1 times x is equal to 0 for all values of x. And quite simply, take x to be equal to 1. Therefore, c1 times 1 is c1, which is equal to 0. And so if you go back, we had a linear combination with three coefficients, c1 times x plus c2 times ln of x plus c3 times e to the x being equal to 0. This was true for all real values of x, and we proved that c2 had to be 0, c3 had to be 0, and c1 had to be 0. And so you see, the only possible linear combination that will give 0 is for c1 to be c2 to be c3 to be equal to 0. Therefore, we only have the trivial solution. Therefore, our three elements are linearly independent. And that's it. So you see, sometimes with more complicated functions, you cannot simply reduce the question of independence or dependence to solving a linear system. You have to sometimes be a little more crafty. And this completes our video.